Hey guys, I'm Jet. Welcome back to my LeetCode review one-take vlog on the 42nd problem, N Queens 2nd edition. The N Queens puzzle is the problem of placing N queens on an N times N chessboard, such that no two queens attack each other. We are given an integer N. We'll return a number of distinct solutions to the N Queens puzzle. Let's see example 1 here. We got emptied N at 4. The output is 2, because there are two distinct solutions to the 4 queens puzzle as shown. Then, let's get into intuition of this problem. We need to find all valid placements where no two queens can be in the same row, same column, or same diagonal, which reminds us of backtracking method. We'll try placing queens row by row. At each row, we try placing a queen in a column, only if that column and its diagonals are not attacked by previous queens. If it's not valid, we backtrack and try a different position. If we successfully place N queens, we count it as one solution. Then, let's consider some approaches. The first approach, I would say, brute force. We can try placing N queens in all possible positions, and then validating each board. But this method is extremely inefficient. Or we can think about the second approach, backtracking with sets or Boolean array. Backtracking with sets or Boolean array. We can place queens row by row. In each row, we can try placing a queen in a column with attack check. And we can optimize the attack checks using sets or Boolean arrays. And then comes to the third approach, backtracking with bit masks. Backtracking with bit masks. For even more optimization, we can use bit manipulation to check occupied columns and diagonals. But let's start with the second approach, which offers a good balance of clarity and efficiency. First, we'll create a variable to store the final count of distinct solutions. It should be a member variable called private integer count. Next, we'll create a hash set to store the indices of columns that are currently occupied by a queen. Private set of integer called columns. Then we create another hash set to store identifiers for occupied positive diagonals, which is top left or bottom right. And the code should be private set of integer called positive diagonal. This identifier we use is row minus column, as is constant along these diagonals. Next, we'll create the third hash set to store identifiers for occupied negative diagonals, which is top right to bottom left. This identifier we use is row plus column, as is constant along these diagonals. And the code is private set of integer called negative diagonal. Alright, let's get into the total n queens method. First, we should initialize the solution count to 0 and the 3 hash sets used for checking occupied columns and diagonals. Columns started with new hash sets. Oops. And positive diagonal gets a new empty hash set. Positive diagonal gets new empty hash set. The third hash set is negative diagonal gets new hash set. And is our count variable gets 0. Then we can begin the recursive placement starting from the first row at 0. We'll declare and implement the solve method in the following code. Solve of 0 and n. After exploring all possibilities, we just return the final count. Return the final count. Alright, let's implement the solve method. This is the core recursive backtracking function. It attempts to place a queen in a specified row. And the code should be private void solve method with 2 parameters, integer row and integer n. First, we'll implement the base case for the recursion. If the current row index equals n, it means we have successfully placed queens in all rows from 0 to n minus 1. So the code is if row equals n, then we'll increment count variable. Since we found a valid solution, so we did it. Count incremented by itself. Then we stop exploring this path and then return. If the current row index is less than n, which means we need to iterate through all possible columns in the current row. For integer column started at 0, when column is less than n, we'll increment column after each iteration. For each column, we need to calculate the identifiers for the positive and negative diagonals for the current square. Integer positive diagonal ID gets row minus column. Integer negative diagonal ID gets row plus column. Now we need to have a check. We check if place a queen at row column is safe. First, we need to check if the current column is already in a column set. And the code is columns dot of contains of column. Second, we check if the current positive diagonal identifier is already in a positive diagonal set. The code is positive diagonal dot contains of positive diagonal ID. Third, we'll check if the current negative diagonal identifier is already in the negative diagonal set. Negative diagonal dot contains of negative diagonal ID. If any of these checks are true, the square is under attack, so we cannot place a queen here. We need to skip this column and continue to the next iteration of the loop. Continue. Otherwise, if the square is safe, we need to place the queen by adding the column and diagonal identifiers to our sets. Columns dot add of column. Positive diagonal dot add of positive diagonal ID. Negative diagonal dot add of negative diagonal ID. We then recursively call the solve method to try placing a queen in the next row. Solve of row plus 1 and n. After the recursive call returns, it means we have finished exploring all possibilities that started with placing a queen at row column. We must now remove the queen by removing the corresponding identifiers from our sets. Columns dot remove of column. Positive diagonal dot remove of positive diagonal ID. Negative diagonal dot remove of negative diagonal ID. This backtracking step allows us to try placing the queen in the next column of the current row. Okay, this is our implementation, and our code got accepted. Let's break down the time and space complexity. So the time complexity consists of two factors. First, the number of potential valid placements explored is bounded by permutations. We have n choices for the first row, and at most n minus 1 for the second, and so on. Second, the contains, add, and remove operations on part set take average big O of 1 time. Therefore, the overall time complexity is roughly big O of n factorial. Then is our space complexity. The space complexity is also made of two factors. First, we use 3 hard sets. In the worst case, each hard set might store up to n elements. Second, the recursion stack depth goes up to n. Therefore, the auxiliary space complexity is dominated by the state and the recursion stack, resulting in big O of n. Alright, this is the end of my LeetCode review vlog on the 50-second problem, N Queens 2nd edition. And I highly recommend you guys to visit my online GitHub page here, which contains all the problem description, intuition, solution with detailed code, and comments. And the final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the codes and nodes to build this online GitHub page. I'll put those two links on my YouTube description below. And thank you guys for watching. See you next time. Bye bye.